In this video we're going to reproduce the paper on adaptive sandwich beam bending, which was published in '96, and it includes an analytic formulation of the bending of a sandwich beam consisting of two aluminium layers which are surrounding a piezoelectric actuator, and there's going to be a voltage difference applied on the actuator, which results in a transverse displacement of the tip of the beam. The paper includes an analytic formulation and compares it to a finite element formulation, and we're going to reproduce that with Quanscient Allsolve and show that we match the results from the paper. So what you're going to learn in this video is how to model a piezoelectric material in Allsolve, how to do a parametric sweep, and where the limit of this analytical formulation is, and when it is better or adequate to use the simulation. So we can change to our simulation environment and create a new project called Sandwich Beam. And first we're going to create our geometry consisting of boxes. I'm going to create one surrounding box and then one box which represents the layer of the piezoelectric material. Okay, so this is how our geometry looks like. And we can continue to the material parameters and to the shared expressions. And I'm going to define one shared expression, which is the voltage difference, and I'm going to set it to 20 for now. I'm going to take from our predefined materials aluminium, but adapt the material parameters to the one that they've been using in the paper. And we're going to select the target region for aluminium. In the next step, I'm also going to take the predefined piezoelectric material model and again adapt the parameters. This one is in the middle volume. Okay, as you can see at the moment, for the predefined material we have a polarization along the z-axis, but what we need in our model is a polarization along the x-axis. We could change the matrix here, but we can also just rotate it in the scripting interface later, and I'm going to show you how to do this rotation in the script when we come to that point. So keep it in mind. Next, we can define the physics. We need solid mechanics in the whole geometry, and we need electrostatics only in the piezoelectric material. We can couple the two physics by applying the piezoelectric material model only in the piezoelectric volume, and we can see the coupling appears now in both physics. We clamp our beam at the left hand side, and we're gonna put and apply the voltage along the piezoelectric material. So first we ground that surface, and then we apply V on the other side using that shared expression that we defined in the previous step. Alright. Now we can already continue and set up the new simulation. It's steady state, including both physics. We can compute it on one node. It's a very simple simulation. We can create a fine mesh, and as outputs we can select the displacement field in the whole geometry, the electric potential field only in the piezoelectric material because we only defined the electrostatic physics in the piezoelectric material, and we can define one other field output which is a custom field output and includes the z component of our displacement field u. Now we can take a look at the script. It's been auto-generated and includes already all the physics here, and as I mentioned, we can edit this script and rotate the piezoelectric material such that it is polarized along the x-axis. We do this after loading the mesh and before setting any field parameters or formulation integrations. So we'll take from the material library our matrix C, rotate it minus 90 degrees along the y-axis, and then set the new value again. Same for the H and epsilon matrix. Also in the scripting we can do some post-processing. So in the end we can compute the deflection along the x position on the beam to compare it to the paper later and save it as CSV files. We can also print out the deflection at the final right tip of the beam. So we're going to interpolate at that right point. I'm also going to define a clock and measure the computational time of the simulation. Okay, that's it. Now we can take a look at the mesh that we produced. It's this mesh, and we can start to run the simulation. The simulation succeeded. We can take a look at the logs. So it's just printing out a total computation time of 12 seconds, and it's printing out the deflection at the final tip, 1.182 times 10 to the power of minus 7 for that one. We can visualize the displacement field. And if we apply or fit the scale factor, we can see that our beam has been bended upwards. We can also visualize the electric potential field. And see that there's just a smooth gradient from 20 to 0 in the piezoelectric material. If we now plot the saved values and then compare it to the ones we get from the paper, so we can see in the paper we have this analytic formulation. We took those material parameters, the geometric parameters of length of 20 centimeters and thickness of 0.8 and 0.2 for the aluminium and piezoelectric material layer respectively, and a voltage of 20. And that is what we would expect from the analytical formulation. It shows the transverse displacement, so the displacement in that direction along the x-axis, so along the length of the beam. And if we now plot our numerical simulation results in the same plot, we can see that we agree with the analytical results, and that we actually, if we compare it to the plot from the paper where they did the finite element analysis, we have the same behavior. So in the beginning we are a bit overestimating the displacement, and in the end of the beam we're a bit underestimating it. Also, if we compare the values at the right tip, for the analytical solution we get 1.196 times 10 to the power minus 5 centimeters. In the paper they get for the finite element modeling 1.179 times centimeters, and for AllSolve we get, depending on the mesh, but roughly 1.178 times 10 to the power of minus 5 centimeters. So they're in good agreement. In the next step, I would like to show you how to perform the parametric sweep. So So we're going to sweep over the applied voltage, and we're going to sweep it from 0 voltage to 100 voltage in 11 steps. So 0, 10, 20, 30, and so on and so forth. And on the right hand side you can see what we expect for as a result, what is the result of the analytical formulation. So if we switch back to our simulation, I'm going to create a new simulation, or actually I can copy the old one such that we already have the changes in the script, and then call it sweep V. And now the only thing to do in order to perform a sweep on V is to add in this sweep and overwrite option to add the sweep over V, and it's gonna sweep over this array. So we're gonna type in from 0 to 100 in 11 steps. If I now start the run, we can see what happens. So we can see in the log files that it started 10 jobs having those 10 different voltages, and those jobs were started in parallel, so they are all running, each one of them on one node in parallel. And we can also take a look at each one of the jobs log output. So they are starting now, and probably they are also going to take around 12 seconds each of them to finish. So after around 12 seconds we're going to have the solution for all the 10 jobs, instead of running them one after each other, which would take 10 times 12 seconds, which is affordable for short simulation, but we can also do that on big simulations, and then it just speeds up, like it speeds up 10 times your simulations, your total computation time. Okay, so also this simulation is finished, and we can take a look. This, for example, job 10. So job 10 was 100 volt, and we can see computation time 12 seconds, and we can see a higher deflection in the Z displacement because the voltage that we applied is higher. We can also take a look at job 2, which is again our 20 volts that we applied, 12.6 seconds, and we can see the same displacement that we've been seeing before. Alright, so we can also visualize those. We can put the displacement field U and then select the simulation that we want to show it. So for the first simulation there's no displacement at all because we didn't apply any voltage, and then the higher we go, the higher is also our displacement V. So if we warp again, we can see that the higher the simulation number is, the higher the voltage was and the higher the displacement is of our beam. Okay, so if we change back to the slides, I again save the results, and now I plotted the final displacement of the right tip of the beam over the voltage. So actually like this final number, this number, but now over the voltage for the 11 simulations that we run. And we can see again there's a good agreement with the analytical solution. As a final step, I now would like to take a look at the comparison of the analytical model to a full 3D and thin beam modeling. So what advantage can we take out of full 3D modeling as we've been doing it so far in our simulation environment. So the analytical model assumes that the normal stress vanishes. So the stress sigma z vanishes, and that there is a state of plane strain parallel to the xz plane, so that the strains epsilon yy and gamma xy, gamma yz is approximately 0. That is what the analytical model assumes, and if we apply it to a geometry that holds these assumptions, the analytical model is valid and fits like real experiment values. However, if we now take a thinner beam, most probably the analytical formulation will not hold anymore because those assumptions will be violated, and that's what I'm going to show you now. So as we already know how to perform these sweeps, I can now sweep on the thickness of my beam. So I can define another shared expression which is called scale y, and this expression is meant to scale this thickness in y direction of the beam. So first we're just going to take it 1, so the same beam as it is, and then I'm going to define a new simulation. I can just again copy this one, call it sweep y scale, and then delete this voltage sweep, but instead perform a sweep on scale y. And now I'm going to just input an array which we're going to sweep over. So we're going to set the values 1, 1e minus 1, 1e minus 2, 1e minus 3, 1e minus 4 for the expression scale y. We also need to use this expression scale y somewhere in the script. So what I'm going to do is I'm going to scale the mesh in y direction using this expression scale y, and just don't scale it in x and z direction. Alright, so that should be it, and we can now run the simulation again. Again, it's going to perform those, how much was it, 5 jobs in parallel. So we expect the results to be ready in roughly 12 to 13 seconds. Alright, so it is finished, and we can take a look at the displacement again. Also, alright, so maybe first we can take a look at the first simulation, which is just the same one as we did for the single simulation without performing any sweep, and we can see that our beam just looks very normal as it was before, and also the displacement is in the range that it was before. Now if we go on to a thinner beam, we can see that now our beam is thinner, but still the displacement looks pretty much the same. Let's apply a bit of a higher scaling factor so you can actually see the difference then. But if we now go to the higher ones, we actually already have a very thin beam, and now we can see that something happens. So what we see is that this displacement is not exactly linear anymore, but it's kind of curved, and I'll show you in the plot that that this is true, and this is like varying from the analytical model. So if we now take a look at this curve, which is basically like again plotting the transverse displacement along the axial location of the beam. So you could imagine it to be like the lower, I can show you like this part of the beam, like the lower line. We can see that for a scale of 1e minus 1 and 1e minus 2, it still fits more or less the analytical model. But then if we go to even thinner beams, we have this bending, curved bending behavior, and it varies from the analytical solution. And that is because we break with the analytical assumptions. So one assumption, if you remember, was that the epsilon yy is approximately 0. And if we take a look at it in the thick beam, that holds. It's just like some peaks at the clamp, but in the beam it holds, that it is 0. If you take a look at the thin beam now, we can see that this actually doesn't hold anymore, but that we have a strain, a yy component of the strain that is not vanishing. And that is why our analytical model breaks down and why we need a full 3D simulation in that case of a thin beam. Alright, so in this video you learned how to model piezoelectric materials, how to perform parametric sweeps on your simulation, and why and when it is useful to model full 3D models and perform simulations on them.